Hi, everyone. Today I'm going to tell you a little bit about the Climate App, which is a tool for teaching people about everything from climate change to the habitability of exoplanets and pretty much everything in between. So this started with Herschel in 1800 with the discovery of infrared light. So there was this light that we can't see with the naked eye, but it can heat things. Then shortly thereafter, Fourier comes up with his idea of the l'effet de serre, the greenhouse effect, that the atmosphere somehow is blocking the heat trying to escape from the Earth. And then you have Eunice Foote, who's much less well known and in fact is only sort of being discovered in recent years, sort of long posthumously. It turns out she was a suffragette, abolitionist, and a climate scientist. So she did a very important study in the mid 19th century where she found that basically carbon dioxide would warm the atmosphere of the Earth. And this all comes to a head in the late 1800s with Svante Arrhenius, who's a Swedish chemist, physicist, physical chemist, and he won a Nobel Prize actually shortly thereafter. And so he wrote this seminal paper about the effect of carbonic acid, which was basically what they called carbon dioxide at the time, and its effect on the surface temperature of the Earth. And what Arrhenius does, which is really novel, is he comes up with a very simple climate model. And it's in fact the basis for the Climate App. The punchline is that in 1896, Arrhenius develops the first quantitative climate sensitivity estimate. If you double carbon dioxide, how much warming do you get at the surface of the Earth? 19th century physics and fairly simple arithmetic and math can lead you to an estimate of the climate sensitivity and can help you understand how planetary climate works. And so that takes me to the Climate App. So here's the Climate App. If you go to the website on your laptop computer or your desktop computer, it'll look pretty much like this. So here it is. On the left, you see the three principal sliders, which I'll get to shortly. And on the right, there's this cartoon, which is, technically this is a trend birth diagram. So this is showing you energy coming in from the star. The yellow indicates visible light, or more technically, shortwave radiation. This is reflected light here. This is light reflected by the surface. And then the red is thermal emission, so infrared light, pretty much thermal infrared light. Here's some thermal infrared light from the surface that makes it out into space. This fat red arrow here is thermal infrared radiation that's absorbed by the atmosphere, right? That's what the greenhouse effect is all about. And then here's the atmosphere radiating that absorbed energy equally up and down. A fun one is the faint young sun paradox. So as we might teach students in astronomy 101, during the main sequence lifetime of the sun, the sun is gonna get a little bit brighter, and that's connected to fusion going on in the core. But the bottom line is that the sun, over the course of billions of years, gradually gets brighter. The inverse of that is that if you turn back the clock and you consider what the sun looked like a few billion years ago, the sun would have been fainter than it is now. And in fact, if you go back to when we think life was originating on Earth 3 to 4 billion years ago, the brightness of the sun would have been about this, 70% as bright as it is now. That doesn't seem like a big deal, but now if you look at the temperatures on the app here, you'll see that the surface temperature would have been, the mean surface temperature would have been 8 degrees below. So we understand enough about climate to know that in such a state, the planet would be fully frozen over. So that's odd, because we also know from geological evidence that the Earth was not, in fact, covered in ice back then. And there was plenty of evidence of liquid surface water back billions of years ago. In fact, some of the oldest rocks we have are sedimentary rocks, which we think formed in the presence of surface liquid water. And so this paradox was known as the faint young sun paradox. So this was first pointed out by none other than Carl Sagan. If the Earth was receiving 70% as much flux from the sun as it receives now, and yet we know that the surface was actually about as warm as it is now, then what gives? Like, what must have been different in the past? And so they can try moving sliders around. They can say, well, what if the planet was more reflective? They say, oh, shoot, that just makes things worse. The planet gets even colder. Okay, well, what if the planet was less reflective? Well, if you make the surface reflectivity sufficiently low, you indeed find that you could get some respectable surface temperatures. Okay, they're getting close to what we have now. The other option is to change the infrared opacity. So again, this is 78% is basically modern day Earth, and now we can see that as we make the atmosphere thicker, as we jack up the greenhouse effect, we can actually eventually get to temperatures above freezing. Okay, and by doing a combination of cranking up the greenhouse effect and maybe invoking slightly lower planetary reflectivity, we can get surface temperatures that are comparable to what we see on Earth today. And it maybe unsurprisingly, these are the two principal solutions to the faint young sun paradox. The number one solution is that there must have been more greenhouse gases in the atmosphere. And it's also plausible that the atmospheric reflectivity was somewhat lower back when life was originating on Earth. Okay, so now let's refresh this. So we go back to the default values. Another application of the climate app is to think about the habitability of an exoplanet. So in order to help us think about the TRAPPIST system, we're going to go to the TRAPPIST-1 webpage, and we're going to scroll down to the convenient table of information for each planet. So here we see TRAPPIST-1b. If I scroll further down, we've got TRAPPIST-1c, and TRAPPIST-1d, and so forth, right? All the way to H. So TRAPPIST-1b, there's a whole bunch of information, but the information that we need for the current exercise is right here, irradiation, okay? So it tells you that this planet is receiving 3.88 as much flux as the Earth receives from the sun. That's what that little S Earth symbol is, all right? And so now we can go to the climate app. So 3.88, keep that number in mind. And what we're going to do, so again, these are the default slider positions. So they're basically in the same position as the Earth. And now we're going to move this to 3.88. Now we don't have that many decimal points. We'll go to 3.9. Okay, so what we see is if TRAPPIST-1b has a similar atmosphere to the Earth, so similar greenhouse effect and similar albedo, similar planetary reflectivity, the surface temperature would be 132 Celsius, so obscenely hot. Now, you can ask, well, okay, what if there was less greenhouse effect? Well, we can just knock it all the way down to zero. Surface temperature would still be extremely hot. By the way, you can also just entirely remove the atmosphere, but having no atmosphere and having an atmosphere with no greenhouse gases from a climactic standpoint has basically the same impact for the surface temperature. Okay, so the planet is ridiculously hot. Now, you could try and jack up the albedo of the planet, and hey, you could start getting to reasonable surface temperatures. So if TRAPPIST-1b had a reflectivity of 70%, which sounds crazy, but for example, Venus has an atmosphere that reflective, but it had zero greenhouse gases, which is very much unlike Venus. In principle, TRAPPIST-1b could be habitable. Part of this exercise is getting an intuition for the two main factors, well, the three factors that affect the habitability of a planet. How much light does it receive from its star? How much light does it reflect back into space, and how much light, how much of the thermal radiation of the planet is absorbed and subsequently re-radiated by the atmosphere? In other words, what is the greenhouse effect on this planet? Those are exactly the factors that actual planetary scientists and exoplanet researchers like myself, those are the same parameters we worry about when we study these planets. And they are exactly the same parameters that matter when you're thinking about the past climate of Earth and the future climate of Earth. So anyhow, I hope you enjoyed this presentation. Again, as a reminder, this is the climate app. So it's at climateapp.ca. If you have any questions or suggestions, please don't hesitate to reach out to me. Thanks a lot.